All right, hi gentlemen. We are going to do another video lesson, and this one is on how to calculate or determine net force. So rather than try to explain it from scratch, I'm going to reference a documentary that was made about net force. It's a very good documentary. It was called Finding Nemo. And there's this great scene in the documentary where they explain net force perfectly. They don't talk about it, they just kind of show you what's going on. So in this one scene, there's a big net, and in the net are a whole bunch of fish. And those fish don't want to really be in the net, they want to get away, can't blame them. But there's this problem, because some of the fish are over on one side of the net, and they're swimming one way. Another fish is on the other side of the net, and they're swimming another way. Another fish is at the bottom of the net, and he's swimming down. And there's another fish at the top of the net who's swimming up. So all these fish are just trying to swim in whatever direction seems like the best way to go from their perspective. The problem is they're trying to get away, and they're really just fighting against each other. Now, it's kind of hard to see in this picture, so what we're first going to do is utilize a free body diagram to really see what's going on here. If you haven't seen the free body diagram video and you need a chance to take a look, go watch that real fast. So I'm going to draw this diagram again, free of bodies. There'll be no body in it. There you go, all done. So that's the net now. It's the net, it's the fish, it's all the stuff in there. I've reduced it all down to a point, so that instead of talking about the stuff that's in there, I can focus on the forces, which is what we care about. So now, let's draw these forces again. There's one fish going to the right, call him fish 1. There's one fish going down, call him fish 2. There's another fish going to the left, fish 3. And there's another fish going up, fish 4. Well, when you look at this picture, you can say, all those arrows are kind of going opposite directions. It kind of looks like these fish are fighting against each other, which they are. So we can actually show that all these forces will cancel each other out. There's two ways to do it. I'm going to show you the not so great way to do it first, and I'm going to show you the much better, more helpful way to do it second. So the not so great way is a way that we've already kind of done with vectors, is to imagine this is like a trip. You're going for a walk, and you're going to go north, and then east, and then south, and then west. And when you take a trip, you have a starting point, and then you go on the first leg of it, or in this case, east. Then you keep going, in this case, south. Then you keep going west, and then you keep going north. And what you find out is that you're right back where you started. Your overall displacement, or your net displacement, is 0. So in this case, all these fish are working against each other, and their net force is 0 because they're kind of right back at the start. This picture is the equivalent of this picture with no forces at all. In both of them, F net is 0 newtons. The total force on the net is 0. The fish are trying to stretch the net, but they're not moving the net at all. Until Nemo comes along. He's the principal researcher in the documentary, and helps them to kind of adjust their strategy to get a more ideal outcome. So let's talk about a better way to do this. A better way that's going to be more systematic, more quantitative, and it's going to be more reliable is, instead of just drawing a picture, we're going to make a table. We're going to have an X and a Y column in this table, and we're going to separate this into two problems. So we take each one of those forces and we say, well, let's put it in the appropriate column. Well, let's start with F1. That's going in the positive X direction. So we'll say plus F1. F2 is going in the negative Y direction, minus F2. F3 is going in the negative X direction, minus F3. And then F4 is going in the positive Y direction, plus F4. Well, that's all of them. So what we can do now is draw a little line across and say, well, in total in the Y direction, we can just add and subtract, can't we? If I'm walking forward and backward, I can just add and subtract because it's in the same direction. And if we assume all the fish push the same amount, then this becomes a big 0 newtons. In the X direction, the same thing, we get 0 newtons. So it's not hard to see that if there's no force in the Y direction and no force in the X direction, there's no force overall. Now, that's an easy example Let's look at one that's a little bit more complicated and apply the same kind of solution to it. So here's a different scenario. We're going to have, let's say, a block, a very fancy block, that's going to get pulled in a couple of different directions. One person is pulling it up and over a whole bunch. Then we also have gravity pulling it down a little bit. And you also have, let's call somebody else pulling it back. So F pull 2 going directly back. And let's say that you have one more force. Well, no, we'll leave it like that. We'll keep it somewhat simple. I can apply this first trick, drawing all my vectors. I don't know how much it's going to help me, but let's try. Here's my starting point. And first I go up a whole bunch on some angle. Then I go straight down. And then I go over. So it looks like my net force, my net displacement is something like that. Right. But that doesn't really help me. I mean, I have to put a whole bunch of numbers and angles in there, do a whole bunch of geometry to figure out how big that arrow is and what direction it goes in. So let's instead try the table solution. So I'm going to get rid of some of the stuff that's in my way. All right. And we'll start by throwing these forces in the table where they belong. So how about F pull 2? Well, that's going in the negative x direction, so negative F pull 2. A force of gravity, that's going in the negative y direction, so negative Fg. But then I have force pull that's not going in the x or the y. It's kind of going in both. Well, we don't like things like that, so let's change it. Force pull is really doing two things. It's going over and it's going up at the same time. I can maybe call this Fpx for F pull in the x direction, and this one Fpy, F pull in the y direction. So now, even though I only drew 3 forces, and really I should have my free body diagram here, you know, F pull, Fp2, and Fg. Even though I really have 3 actual forces, I can treat them like 4. I can say, hey, it's easier to think of pull as one going over and one going up. So let's do that. We'll put it in our table. In the y direction, I have a positive component of the pull, positive F pull in the y. And in the x direction, I have a positive F pull in the x, Fpx. That's positive. Well, that's everything, so I can add them up. Now, again, the y's add really easily. And I don't have numbers for them, so I'm just going to say, well, I can't say that they definitely cancel out. I'm not sure. They don't look like it. So let's just say I add them up. We have a symbol that we use in math and in science that says add them up. It's this. It's the Greek letter sigma, which I did a bad job drawing. Looks like a big capital E, but it's the Greek level sigma. So add up all the forces in the y direction and add up all the forces in the x direction. Well, that doesn't really help me. Now I have a force in the x and a force in the y. You know, so what do I know now? I know in total I'm getting pulled over a little bit. Let's make this bigger too, shall we? I don't know why I drew a small version to begin with. So we'll make our free body diagram, draw this real big, and have a better vision, or better image. There's F pull, then here's Fg, and then here's Fp2. We said, well, the net force is start to finish. There it is, something like that. That's F net. And what we just calculated here is how much F net points in the x direction, sum of the forces in x, and how much it points in the y direction, sum of the forces in y. Well, if we have those two parts, it's pretty easy to get F net. We've done this 100 times just with different symbols. Slap Pythagorean's theorem on it, we're all done. So what we find out is F net equals the skirt of sigma Fx, so the sum of all the forces in the x direction squared, plus the sum of all the forces in the y direction squared. Now, if we go backward and apply this to the Nemo situation and say, hey, these canceled out, so the sum of forces in the y was 0. These canceled out, the sum of forces in the x were 0. 0 squared plus 0 squared is 0 squared is 0 is 0. My favorite number. We're all done. FNet 0. What if, though, what if instead of these purple fish all swimming in different directions, what if, say, 4 of them decided to swim straight down? 1, 2, 3, 4. Well, now I would have 4 forces in the x direction. I'd add them all up, square them. There would be no forces in the y direction, so that would be 0. So sum of the forces squared and square rooted just equals sum of the forces in the x direction. So if each of these were a 1 Newton force, my FNet would be 4 newtons. It's not really complicated. The same stuff we've been doing. We're just using the letter F instead of velocity or instead of displacement. Hope this helped. Bye-bye.